So, we have almost completed the chapter on central force motion. We started with the definition that force on a particle is towards the origin or away from the origin along the radial direction and depends only on the distance of the particle from the origin. Then we say that it is central force. Of course, we choose our origin in appropriate manner. Okay. And then we saw that the motion will be in a plane, and then we talked of several kinds of energy diagrams and when the motion will be bound, unbound, all those things. This inverse attractive attractive force, we talked at length about that, because that is very important. All the planetary motions and other things are governed by this kind of law. So, all those things we have done. Last piece, because whenever in nature there is a force, the force is exerted not by the origin, but by the object, by some object. That object may be placed at the origin, but nobody is holding it there. So, if this object at the origin is exerting a force, central force on my particle, the particle is also exerting force on this bigger object or the object at the origin, and therefore, this will not stay there, and hence it is a two body problem. Small m is moving in because of the force by the capital M, but then the capital M will also move because of the force from this small m, and therefore, keeping the body body at the origin, that is not the case. Of course, I can put the origin on the body even if it moves, but then that becomes non-inertial frame, and all our equations are for inertial frames. But it so happens that this two body problem can be reduced to one body problem, and that one body problem is exactly the same which we had been describing with a fixed center of the force in an inertial frame. Let us see how. So, suppose I have an inertial frame, this is our inertial frame S, and then I have some object here, let us say of mass m1, and another object somewhere, let us say at certain instant, this is at some other position, mass m2, and I call this position vector as r1 and this position vector at r2. These two objects, they are exerting forces on each other, and that force is directed, force on m2 by m1 is directed along this line joining, and so is the case when you consider force by m2 on m1, and the magnitude of this force or these forces is dependent only on this separation. So, if I put my origin here, okay, I am satisfying the conditions of the central force. The force on this m2 is always towards or away from the origin, and the magnitude of the force is dependent only on the separation. So, I am satisfying all those conditions. Only thing is that then if I put the origin here, then my frame becomes non-inertial. Okay. So, this is the situation. So, force on m2 by m1 is f of r and in r cap direction, but now what is r cap direction? Is the unit vector in the direction of r2 vector minus r1 vector. this is that vector, this vector is r2 vector minus r1 vector, this vector here, and the force is in this direction. It can be negative, it can be this way or that way. So, force is in this direction. If it is attractive, it is opposite. If it is repulsive, it is like this. Okay. So, this is that r cap vector, and the magnitude of the force is dependent only on this r. This r is separation between these two particles. So, this r here is r2 minus r1 vector, magnitude of this. So, this is the situation, and opposite force on m1 by m2, Newton's third law, is minus of Fr and r cap. So, how do we discuss motion of m2 and of m1, because it is a two body problem, both are moving, both are accelerating, and therefore, to consider that motion we change variables, because we are interested in motion of m2 as seen from m1. So, we change our variables, we define r as a center of mass, m1 r1 plus m2 r2 divided by m1 plus m2, and the other one is this r, we define this r as r2 minus r1, as if my origin is here and I am writing the position vector of this with respect to this origin. So, this is r. So, we define these two. The motion of or change, rate of change of this r and the corresponding accelerations are trivial, because if it is an isolated system, the center of mass either remains at rest or moves with constant velocity. So, from the initial conditions I know what is the situation, and so where the center of mass will be at time t, simple. So, what we are really concerned with, this particular thing. Now, let us see, if this is r, what is r double dot? What is r double dot? R double dot is, that means the second time derivative acceleration. R double dot will be r2 double dot and then minus r1 double dot. And what is r2 double dot? R2 double dot, this is r2 in an inertial frame, this is r2, and double dot the acceleration of this particle as seen from the inertial frame, that will be force divided by mass. So, m times r2, m2 times r2 double dot is equal to the force and so mass I have written here. So, mass m2 and into acceleration of this second particle in an inertial frame of reference, because r1 and r2 are measured from this inertial frame of reference, should be equal to force on this, and force on this is only because of this m1, and that is Fr r cap. So, this is Fr r cap. So, r2 double dot is Fr r cap divided by m2, and similarly m1 r1 double dot, acceleration of the first particle as seen from the inertial frame of reference and multiplied by mass should be Fr r cap with a minus sign, Newton's third law. Force on m2 because of m1 and force on m1 because of m2, they are equal in magnitude and opposite in direction. Our r cap vector is already defined, this is the unit vector in the direction of r2 minus r1. So, on m2 it is r cap and on m1 it is minus r cap. Of course, this Fr can be positive or negative, that will depend on whether it is attractive or it is repulsive. Okay. So, r1 double dot is equal to Fr r cap minus sign and divided by m1. Put it here, what do you get? you get r vector double dot is equal to r2 double dot is f r r cap divided by m2 and then minus, and then you have r1 double dot which is here. So, another minus and f r r cap divided by m1, right. Now, this is equal to 1 by m2 plus 1 by m1 times f r r cap. This is m1 m2 here, m1 plus m2 here, and then f r here and r cap here. So, you can take this on the left hand side, write this as some number mu, write this as mu, and you have, or m, let us write it m. Let us write, we have not used m as such, we have used m1, we have used m2. So, let us write this as 1 by m, okay. Let us write this as 1 by m, dimensions. Here it is m1 plus m2, here it is m1 into m2. So, it is 1 divided by mass. So, let us write this quantity as 1 by m and take this m on the left hand side. M times r double dot, m times r double dot is equal to f r r cap, where m is equal to m1 m2 divided by m1 plus m2. And what is this equation? This is the equation that we have solved in the previous lectures. You have an inertial frame, you have this inertial frame, and here is the origin, and just one single particle here of mass m, and somehow this origin is exerting force on that m, and that force is dependent only on this distance from the origin, and it is in the radial direction, it is f r r cap. This is what we had done. What will be equation of this particle in this inertial frame of reference? That will be mass into its position double dot, mass into acceleration is equal to f r r cap. So, if I know how to solve this equation, I know how to get the motion of m2 as seen from m1. So, we fix up our coordinate system on m1, and then wherever this m1 goes, my coordinate system goes. We are not rotating this axis system, but the origin is shifting from here to here, here to here. As m1 moves in influence of the force from m2, this origin keeps shifting. So, it is an accelerated frame, but we do not have to go for the techniques of non-inertial frames. Our next chapter will be on non-inertial frames, and I will be discussing what are those techniques, but we do not have to go into those techniques. We can still use our techniques of inertial frame of reference. Consider a particle m, just one single particle, and it is acted upon by a force f r r cap, which depends only on the separation of the particle from the origin. Somehow we have fixed this object which is exerting force at the origin of this inertial frame of reference, okay, and then solve what will happen to this particle, and that will be the motion of this particle in this non-inertial frame. The only thing I have to do is, in place of its mass m2, I have to use another mass m, which is given by this equation, which depends on both the particles, the one which is exerting the force and one which is experiencing the force. Okay. So, this is given the name reduced mass of the system of two particles, of the system. it is reduced mass of the system. So, if you want to get the motion of m2 with respect to m1, use this, and of course, m1 m2 you can interchange, you can get the motion of m1 as seen from the frame which is fixed at m2, that also you can do, and similar thing with a negative sign. So, this is how the whatever we had done is very practical. And if suppose m1 is very large, suppose this m1 is very large as compared to m2, what happens here? If m1 is very large as compared to m2, in that case here m1 plus m2, you can neglect this m2. Okay. Of course, you cannot neglect it here, you cannot say that okay, let us say m2 is close to 0 and therefore we neglect it, you cannot do it here, but here you can do m1 plus m2. So, if you neglect this m1 cancels out, and then this m is almost same as m2. So, if one of the particles is very heavy as compared to the second one, then you can still use the same equations, and you can use the mass of this particle as such m2. This reduced mass is almost same as m2. So, in the sun planet system, for example, sun is very heavy as compared to earth. So, if you are not doing very sophisticated calculations like that precession of perihelion of Mercury and so on and so forth, for usual kind of astronomy, you can treat the sun as an inertial frame of reference, not being influenced by the presence of earth, or proton electron system. If you are doing Bohr model, you can do all those kind of things, but even if they are not too different in the masses, even if there are comparable masses, even then we can use this reduced mass and use all the equations that we had developed for this particle motion under a central force. So, that finishes our chapter on central force, and now I will be going for next chapter, which is non-inertial frames. So, I had already talked about inertial and non-inertial frames. The Newton's first law is kind of a definition of a inertial and non-inertial frame. If f is 0, that implies that the acceleration of the particle is 0, and if acceleration is 0, that implies that force is 0. So, this is cryptic statement of Newton's first law, and if this law is followed in some frame, that frame is called inertial frame of reference. Right. So, all those things we know very well, and if it is not, then it is non-inertial frames. So, in non-inertial frames, the second law is also not valid. The second law, Newton's second law, is not valid. F, resultant force F on the particle is not equal to mass of the particle times acceleration of the particle in such a frame. There are frames, we know there are frames in which this does not, it is not valid, and if it is not valid in those frames, this is also not valid. And then we can say that F and minus m a is not 0, is something else. What is that something else? That something else is written as something. So, let me write it f p, okay, or minus f p. So, mass of particle into acceleration of the particle is equal to f and plus f p. If it is an inertial frame, mass into acceleration is force, but if it is not an inertial frame, it is a non-inertial frame, then mass into acceleration is not F, and what is left is written as Fp, and that we called pseudoforce. Why do we call it pseudoforce? Because if you bring it here, it is not there. Okay, this is the resultant force, this is the resultant force, all the forces which are acting on the particle are included in this, then nothing left. When we say F equal to ma, when we write Newton's second law, F equal to ma, this F includes all the forces which are acting on the particle. So, it contains all those forces, it is resultant force, still it is not equal to m times a, and that is why we have to add something else to make it equal. And why are we so interested in making it equal? This is because we have learned all the techniques of how to solve this F equal to ma. Okay, we have done hard work to understand that in a given situation how do I apply this F equal to ma, and from there how do I get the path of the particle, position of the particle, velocity at the particle, acceleration of the particle at any given time. We have learned all those techniques that are governed by this equation, and we do not want to lose that advantage. So, we bring in from our side some extra terms, make the right hand side equal to mass times acceleration, and then use all these techniques of inertial frames of reference, and we can get motion of the particle in that non-inertial frame. So, this is how the pseudo forces are operating. Now, acceleration of the frame, you have two broad kinds of varieties, two broad kinds of non-inertiality. So, one is when you have translational acceleration, of the frame with respect to some inertial frame. Okay. So, we assume that okay, we know at least one inertial frame, our laboratory, our room, our earth, our roads, they provide us a reasonably good inertial frame of reference. So, I will be talking in this course the non-inertiality of earth because of its rotation, but if I am driving, if I am running, if I am swimming, if air is blowing, many of the things can be reasonably well understood, calculated, predicted using earth as an inertial frame of reference. So, anyway, suppose we do have an inertial frame of reference and then there is some non-inertial frame, that non-inertial frame will be accelerated with respect to this inertial frame, because any frame which is moving with uniform velocity with respect to an inertial frame is also an inertial frame. So, if it is non-inertial, it has to have an acceleration with respect to some inertial frame. Translational acceleration, that means if this is the inertial frame, let us say this is the inertial frame, and then I have yet another frame, it is translating with respect to this. That means the origin is here, and if it is moving, all the particles fixed in this frame, axis, everything, anything which is fixed in the frame has same velocity at that instant. If this is having this velocity, 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 right. If the velocity is upward, then everything is going upward. So, axes are not rotating, they are only translating. So, that we say translational acceleration. So, first let us see, if my non-inertial frame is translating with respect to the inertial frame and then there is an acceleration because now I can talk of acceleration of the frame. All the particles of the frame, all the points of the frame which are fixed in that frame, they will be having the same velocity at any given instant, and therefore the same acceleration at any given instant, and therefore I can talk of acceleration of the frame as such. So, in that case, what kind of pseudo forces we need? So, I will show you a small video clip. It is taken from my course on special theory of relativity, and you see the video. I will be describing it here. So, let us see what happens if you have a non-inertial frame which has translational acceleration. So, I am trying to show non-inertial frame which is on this box, and on the lid itself I have drawn x axis, y axis, and z axis is upwards, and in this box this is x axis, y axis, and z axis upward, and then in this box you can see a ball hanging in water. So, the thread is fixed at the lid. So, at this time the ball is at rest, and x, y, z, nothing is changing. What I will do, I will be giving this box acceleration towards left, my left, and you have to see what happens to this ball, in which direction this ball moves with respect to these axes, whether it goes to the right or to the left. Here it is. You have seen I took the box towards left, but the ball moved towards right as seen from this origin, this xy axis goes towards the right wall. So, what has exerted force on the ball in the positive x direction? No one. We had taken this box towards left, but the ball is going towards right. So, this is a non-inertial frame. No one to exert force on the positive x direction. Water can exert a force in horizontal, but that will be in the negative x direction. There is no one to exert force on the x direction, but the ball is going in the x direction. But we want to use Newton's laws. If the ball has gone towards right, there has to be a force towards left. So, we accelerate the ball towards left, and we say that time there is a force on the ball towards right, and that assumed force which is not there in the box frame, box goes towards left, there is an assumed force towards right, and that force is the pseudo force. Only to use Newton's law in the non-inertial frame, we have to take some extra force which is not there. If this box is going towards left, then we have to take the force towards right, opposite to the acceleration of the frame with respect to inertial frame. That is our pseudo force. So, you had seen that I had accelerated my frame. I have given a translational acceleration in the negative x direction, and it created an acceleration of the ball as seen from that translating frame in positive x direction. So, we will do more algebra on it in the next lecture.